Okay, thank you, Leo, for inviting me, and also Manuel, Pablo, and Santiago for organizing. This is based on joint works with Oriane Blondel, Frank de Hollander, Daniel Kills, Renato dos Santos, Vlada Sidora Vicius, and Augusto Teixeira. So I will tell you a little bit of some results that we have obtained in the last years about this random walks on dynamic random environments. So just in order to fix a little bit the setting, let us assume that we have down here random configuration of particles. So each site on Z, let's say, can be either occupied or vacant. So you have this configuration of particles, or you can alternatively think of a profile of height here. And then you have a different particle or walker that it's gonna evolve randomly on this profile or in this height profile. And let us assume that it always has a drift downhill. So if it's here, then it have a drift down there. If it's up here, then it has a drift down there. Or you can think that this person carries two different coins, one with parameter P occupied in between 1/2 and 1, and this one with parameter P vacant between 0 and 1/2. And then it uses one coin or the other, depending on whether it's on top of a vacant site or a particle. And then if you just freeze your environment here, this is going to be an instance of a random walk on a static random environment. But in this talk, we will be interested in letting these particles evolve down here, or the environment evolve down here. So for instance, if this particle jumps here, then this height profile is going to change, or maybe this particle jumps here and then the profile changes here. And then at the same time as the walker is evolving, the environment is also changing. Just still in the case where environment is frozen, so it doesn't change. This has been studied long ago, since the seminal paper of Salomon in 75. And many other people in Dimension 1 work with this, including Kasten, Kozlov, Spitzer, and Senai. And there is this very interesting phenomena that it's related to trapping, because if you are in a region between occupied sites and vacant sites, then you have a drift to the to opposite sides here, and maybe you're gonna waste lots of time in this region, in this interface between these two areas. And this leads to very interesting results, like for instance, transient regimes where you actually have zero speed, so you go much slower than linearly because of this trapping. And it's fair to say that in Dimension 1, this is fairly well understood. So people have constructed very refined criteria for transience and recurrence. Also, law of large numbers, central limit theorem, and the several large deviation results. In Dimension 2, this area with static environment, it's still very active. There has been lots of progress, and many people in this audience are experts on the field. I am not, so I will not mention results about this. So let me move to the actual dynamic environment. So as I mentioned, I will let in this talk the environment evolve. So maybe this guy was in this particle here, and it decided to jump left using the coin P occupied. And when it lands here, then it's a vacant site, then it's going to use a different coin. But maybe now when you come back to the site the person started, then the site is no longer occupied, then you're going to use the different coin here. And then I will just mark it in this talk as x of t, the position of this person at time t, this walker at time t. So I hope it's clear the difference in between static and dynamic random environment. And just some comment, quick comment here is that it's not clear whether these traps are very relevant in the case of static dynamic environment, because the traps itself, they dissolve, they, as time evolves, they just disappear. So anyway, we want to study whether we can obtain law of large numbers, central limit theorems, and the interesting phenomena as in the static case. So the study of dynamic random environments has started much more recently if compared to the static, and I will comment on previous results afterwards. But now let me just fix some notation and for this talk, and I will be mainly interested in cases where the state of space is it's countable, and let's say most of the talk it's going to be either occupied or vacant, but you can think of some other state spaces. And actually my running example, or the examples that are in my mind are kind of interacting particle systems like contact process, exclusion, systems of independent random walks, or the zero range processes. And you could in principle think of a much more general setting, like you have a process, a spatial process, or a space-time. So this is time up. So you have some configuration in the plane, and then you release your walker. So it goes, of course, ballistic to in the direction of time, it has to go up, but then following rules that depend on the environment. And I will come back to the walker very soon. But the main assumption about the environment is going to be invariance under space-time shifts. And as we're going to see, the results that we can obtain will depend a great deal on the mixing conditions, extra mixing conditions that we impose in this random environment. So as for the random walk, for this talk, I will only consider discrete time and dimension d equal to 1. And this is just that the jumps are decided locally. So you just take into account the environment exactly at the place where you are. Of course, you can lift this assumption and look to a finite box around your current position in order to decide the jumps. But in this example that I started with, it's a very simple function of your current position, okay? So as I mentioned before, the results that we obtain will depend mostly on the mixing conditions that we impose on the environment. Okay, are there any questions about the setting for the moment? Oh, okay, so if not, let me just mention a little bit some previous results. There has been lots of work about this since the years 2000, and I don't intend to mention all of them, but here, the simplest type of environment that you could think it's the one that refreshes completely at each time step. So you have IID in space and IID in time. And if you think carefully under the annealed law, when you average on the environment, this is just simple random walk, and then you know everything about it. But there are very nice results about quenched CLT by these people here. And then after that time, after years 2000, also these people and other people started to think of correlations in time. So you could try to set the environment to be a Markov chain on the top of each site. So it's independent in space, but Markovian in time, for instance. And under extra assumptions, like people like Dogo Piacci, Keller, and Liverani, and many others were able to prove central limit theorems for these walkers. But let me mention one work that inspired us a lot, and it's a work of Luca Avena, Frank de Hollander, and Frank Reddy, where they tried to obtain, or they obtained more robust and general assumptions on the environment, on the mixing of the environment that could allow for time and space correlation. So this is the cone mixing environment, and it's also inspired in a previous work of Comets and Zaitouni. And the condition is that for each cone like this, with an opening theta and a height separation from the p equals 0, let's say this half plane here equal to n, the separation, then the probability of one event supported on the cone conditioned on an event supported on the half space minus the probability of the event without conditioning goes to 0. And this has to hold uniformly over the choices of events up here and down here. So this is one instance of what we call uniform mixing. So it's nice because it gives us like something that, oh, you only have to check this assumption about the environment and then you get the results. But on the other hand, it's assuming this kind of uniform mixing for the environment. And for instance, if you think some process like the contact process, we're not immediately satisfy this, because if you have a very large empty region here, then it's not likely that a particle is gonna, the infection is gonna get here. Nevertheless, there has been several other works in specific kind of environments, like the supercritical contact process and others that I will mention later. And then I just wanted to mention that for the contact process, there is this work of Renato and Frank, Tom Malford and Eulalia, where they obtained the law of large numbers. So these are different works, but overall, they obtained law of large numbers and central limit theorems for any dimension and in quite a general setting. So let me now move to the environments that we studied with my colleagues. And so one of them was this setting of independent random walks. So you can think that you start with initial configuration, eta 0 of x at each site x. And this is a Poisson random variable with parameter rho. And you think of this rho as being kind of something parameterizing the density of the environment. And then once you have the initial configuration, you just let every particle jump, performing an independent simple random walk. And then you have the same setting as before, 2 coins that you use in order to decide how to jump depending on the environment. And then let me just call V occupied and V vacant the corresponding drifts. And let us assume that the drift to the right on the top of particles is bigger than the drift on top of holes. So maybe you have an empty site like this one. So you have a drift. And let's say the interesting case, it's when the drifts have opposite sides. So let us assume, for instance, that this guy here is negative. And here we worked mainly in the regime where the densities are very high. And what we could prove is that if you make the density high enough, then there exists some velocity v, such that you converge to this velocity, to this speed almost surely under the annealed law. Okay, and you have normal fluctuations. Actually, we can prove that you converge as a process to the Brownian motion with a certain non-degenerate variance here. So the techniques that we used in order to prove our results are based on two main techniques. So one, it's renormalization. So we use we analyze this system in multi-scales, and we use this in order to prove that the Walker is going to be ballistic for large values of the density. But this is somehow natural, because you just, if the density is very, very high, then every site has lots of particles on top of it. You are going to be on top of particles most of your time. Very rarely you're going to find a trap, and then we could use this technique in order to show that first you are ballistic, and once you are ballistic, then since information in your environment, it's only diffusing because particles perform random walks, then you left all the information that you collect about your environment behind, and you can construct a regeneration structure in order to obtain law of large numbers and central limit theorems. Drawback is that it's a perturbative method, because we can only allow for densities that are very high, and this is somehow related to our renormalization method here. Somehow we have to trigger some sequences of inequalities, and for that we need to use that the density is very high. We also worked for density close to zero. It's a little bit more complicated in this case, and also for higher dimensions and density close to infinity. Another model that we consider now with Daniel Keels and Augusto Teixeira was the exclusion processes, playing the role of the environment. So you let particles just, or edges, just change their occupation in their end points at rate lambda, gamma, independently, one of the other. And then this gives rise to the exclusion process. And again, we use 2 coins in order to decide how to jump. And here the equilibrium measure for the environment, it's just a Bernoulli of parameter rho, which I will understand as being the density as well. So before our work, there has been also lots of interesting works on this direction, and they are all perturbative in some sense, because, for instance, Avena, Dos Santos, and Vollering, they consider the case where you already have a uniform drift that it's positive and high enough so that you leave information of the environment behind, and then they were able to construct a regeneration structure and prove CLT. Renato has some works as well where the density has to be either very low or very high, and he compares this with the homogeneous random walk. So also this work of Francois Simenon and Francois Houveniers, it's very important for us. Actually, it's perturbative on the rate of the environment. So they consider either that the environment changes at rate very high, so you only see an average of the environment, or the opposite case where the environment is freezing, so you're kind of converging to a static random environment. And they were able to prove law of large numbers and central limit theorems in these extreme cases, using ideas that are very similar to our work here. And it was more or less on the same time, 2015, and it was somehow very similar. They also use a renormalization in order to obtain ballisticity or transience, and then they build a regeneration structure. So it's very similar, and I will come back to this result shortly in this talk. Our theorem about the exclusion process is this one. So we assume that the probability to jump to the right on top of particles is bigger than the probability of jumping to the right when you are on top of holes. And then in this situation, we have shown that there exists no increasing function, V, that takes one density and assigns an potentially speed, okay? That it's non-decreasing in the density. And moreover, there are two special points, such that for every value of the density that are not one of these 2 points, then you have a limiting speed that is given by this function here. Moreover, in case these 2 values are different, one from another, then you have the speed 0 in between them. And for any value of the density outside this interval, then the speed is different from 0 and more than just the law of large numbers. You have also a central limit theorem that can also be made functional, and we can prove that as a trajectory, the random walk converges to the Brownian motion. So let me just mention some possible shapes that this function V of rho could in principle have. So we have these 2 different values, rho minus and rho plus, and in between them we already know that speed is 0, and outside this interval speed it's positive, and we actually don't know whether there is a well-defined speed at this point. So at this point, we don't know anything. It could be the case that actually these points are the same point, and then we don't know if we have speed here, all right? But in this case, we would have V positive here and V positive here in the central limit theorem in these areas. But we actually believe that the picture should be something like this on the right, okay? Where you have only one point where the speed is 0, then you would know law of large numbers for all values of rho. The only point where it is 0 is here. And for these regimes here, we would have CLT, but not here. So where speed is 0, we cannot prove central limit theorem. Okay, so we actually don't know how to prove strict monotonicity for this curve here. And also the same result extends for independent random walkers instead of exclusion process. So one interesting special case of our results is when you are in exclusion process again, and the density is exactly equal to 1/2. So the thing is symmetric. The role of the holes and the particles in the environment are symmetric. And we also take symmetric coins. So the drift on holes is exactly minus the drift that we would have on particles. And in this case, we are able to show that the speed is equal to 0. And this is a result that we were quite happy when we obtained this, because when your speed is 0, you could think, okay, you come back, or when you're in a symmetric situation, you could think, okay, let me show that I come back to the origin very often, and then show that try to show some regeneration structure that I forget about the environment, and then show that my speed is 0. But this is kind of complicated because the environment is not mixing well here. So you come back to the origin, and then you would have to control again the information that you have collected about the environment, and this is difficult to do. And we find a nice way around this. I don't know how, so I think I have like 3 minutes, right? So I will try to give a very, very rough idea of the ideas that we use in the proof in this last 3 minutes. And well, I hope that at least some of the ideas are going to be clear. And so the important idea here, it's based on the work with Oriane Blondel and Augusto Teixeira in 2012. And it's related to what we call deviation events. So we take a box of a height h, and let's say length 3 or 5h, something like that. And we'll fix a reference slope, this one here in blue here. And once we have this reference slope, we look at the event that starting a random walk from this middle interval, it's gonna end on the right of the slope v, all right? And the same thing to the left, then I put this tilde here. So deviation to the right here, and deviation to the left, this one here. And then the probability of these events I will call pH of V and the pH tilde of V. Then we define two kind of critical speeds here. So this is really inspired in critical points for percolation. So you take the minimum value of V such that the probability of deviating to the right of it starts to get very small. So let's say if you have this slope here and you push to the right, it gets harder and harder to go faster than this. So there should be one point where above it, the limit goes to 0, all right? And same thing for deviations to the left. We define the maximum of a V such that the probability to deviate to the left of it goes to 0 as you increase your boxes, okay? So what we want to show is some kind of, use some kind of bootstrap in order to show that since above V plus, it decays at some rate, then it has to decay fast. And the same thing to the left, if you are below V minus, since it decays, then it has to decay fast. And then if these two values are different, then you have some region that is somehow critical. You should go with speed sometimes close to V plus, sometimes close to V minus in some sense. So our idea is to first bootstrap and show that you have fast decay above V plus and below V minus, and then show some kind of sharpness that actually these 2 points have to be the same. And then if these 2 points have to be the same, you cannot go faster than it, you cannot go slower than it, then you have to go at this speed. So, let me just take one more minute in order to show how the idea goes here. It's a classic renormalization where we choose growing scales of boxes like this, and one scaling factor, h. And we assume that the event happened at scale k plus 1, and show that there are 2 places in scale k that are well separated where it also has to happen. And then what you have is some sort of contracting inequality that shows that the probability of having the deviation in a higher scale, it's smaller than an entropic factor times the probability of having it in the smaller scale square. And there is an error coming from the covariance from these 2 boxes here. But if this is small, then you are fine, then it's contract. So this is the idea in the work with Oriane and Augusto. And then with Daniel, we were able to extend this for models like the exclusion process. So I think I will stop here because I have gone over time. So thank you for watching, and that's it.
Thank you, Marcelo.